Hello students, in the last session we completed around 10 sums that were related to fictitious forces and motion of car on a circular road and banked road, all those things. Okay, same way in this session we will do the next 10 sums. So these 10 sums will also be related towards fictitious forces and then the circular motion and those stuff. Okay, so let's see what are all the next 10 sums. So now let's jump into the 31st question. Okay, so this question is straight away simple one. Let's see what the sum is. Two stones of masses m to m are wheeled in horizontal circles. Okay, so you got like two stones, one is like m and other one is double the times of that mass. The heavier one in a radius r by 2 and the lighter one in radius r. Okay, so let me draw the diagram for it. So you have got a mass over here. This is wheeled, this is the lighter one. It is wheeled in a radius of r and the mass is like m. Okay, so the heavier one is actually having a mass of 2m. It is wheeled in a radius of r by 2. Okay, so that is how we are going to swing both those masses. Fine. So then what they have given over here is the tangential speed of lighter stone is n times that of the value of heavier stone. Okay, so then they have given us the relation between the tangential speed. Tangential speed is nothing but the linear velocity, right? So what they have given here is the tangential speed of the lighter stone. So let me make it this way. The tangential speed of the lighter stone will be represented by v subscript small m will be equal to n times that of the value of the heavier stone. N times that of the value of the heavier stone, which will be like v subscript 2m. Okay, straight away I just changed that statement exactly into an equation. That's it, finished. Okay, so the hint over here is they experience same centripetal force. So they experience same centripetal force, which means F centripetal in the case of the mass m will be equal to that of the F centripetal of the mass 2m. So these two stuff are just the same thing. What they are asking us to find is actually the value of ns. So what will be this n? That's what I'm supposed to find here. Okay, so the hint over here is actually F, the centripetal force experienced by the mass m will be equal to that of the centripetal force experienced by the mass 2m. Okay, so these two things are going to be just the same. Got it? So in the case of the first thing, let me substitute the mass and everything. I'll end up getting the n. So for F centripetal, I will be able to substitute m v square divided by r. So the velocity here is just the same thing, f m v square divided by r. The radius will be the same radius. Okay, for the mass 2m, the mass will be like 2 times m, velocity will be like velocity 2m the whole square divided by r. R will be half times of this r, that's why it's going to be like r by 2. Okay, so here you will have like r divided by 2, right? Just rearrange it, you'll get the answer straight away. M will get cancelled out, or r will get cancelled out. Instead of vm, I'll substitute like n times 2vm, n times v2m. So you'll have like n v2m the whole square, which will be equal to 4v2m square. Okay, so these two v2m's will get cancelled out. So n square will be equal to 4, therefore n will be equal to 2. The answer here is 2. N is equal to 2. Got it? This is just a simple one, straight away sum. The option is option 3. Fine. You shouldn't have any doubt in the sum. Simple, straightforward, easy sum. Let's move on to the next one. This sum is based on the fictitious force. Let's see what the sum is. A car is moving in a circular horizontal track of radius 10 meter. Okay, so that is a car which is moving in a circular track and the radius is like 10 meters. Fine, with a constant speed of 10 meter per second. Got it? Data related to the velocity and then the radius is given over here. A bob is suspended from the roof of that car by a light wire of length 1 meter. Okay, so there is a bob which is getting suspended inside the car by a wire of length 1 meter. Okay, so there is a kind of pendulum inside the car. That's what they have given over here. Then the angle made by the wire with the vertical is, so when it is about to make a circular turn, obviously the circular turn is made from the reference outside. Okay, so when it is going to make a circular turn, friction between the tire and then the road gives you the centripetal force. So what will happen inside the car? Inside the car, obviously it will be like the other way around effect, right? So that this is the question, this the same pattern question we have seen in the last session, as if like a circular drum which is revolving in a circular motion, rotational motion. In that situation, I got like an extra object inside that circular drum. Okay, so it's a kind of same sum over here, same logic over here. The thing is, here instead of that instead of that block, here you have got like a pendulum that is hanging inside a car. Obviously, whatever experience that you feel from the outside, it will be like whatever stuff that is happening outside, you will feel an experience that is opposite inside the frame of that reference, right? So same thing is going to happen over here. Here I've just got a car. Okay, that is, yeah, let me put it this way. I've got a car, fine, something like this. Yeah, so don't get me with the diagram. So you have got like a car that is going to move in anti-clockwise direction in this situation. Okay, so in this situation, it is going to turn towards the left. Okay, so if it is turning towards the centripetal forces acting inwards, then what should be the centrifugal force that is acting inside the frame of reference with respect to that pendulum bob? It will be like opposite, right? So in this case, I'm just giving a force that is acting, acceleration is towards the inwards. Then inside the frame, the acceleration should be outwards. Okay, it should be like radially outwards. Okay, so here it is towards negative I cap. Then obviously the pendulum that is hanging inside the car should move towards the right side. Okay, got it? Those two things are oppositely related, right? Something like that. Okay, counterintuitive thinking, it should be clear. So here I have got a pendulum that is inside the car. Okay, something that is hanging inside the roof of the car. So that's going to move towards the right. As the car is turning towards the left, it will experience a centrifugal or fictitious force that is going to act towards the right. Okay, both will be like opposite to each other. Got it? It should be clear. So if that was the case, the pendulum will be at certain inclination, and then yeah. So when you consider this stuff, so this will move towards the right, and this will experience an acceleration of v square by r. Same acceleration, whatever acceleration that it acted inwards, it will experience same effect in the opposite direction. Got it? So here if you look, it will have an acceleration outward of v square by r. If I just convert it to force, I'll have to multiply it with the mass of that particular bob. Okay, so the mass of the bob was like m, right? So that's what they've given, right? Now they haven't given anything related to mass. Anyway, it will get cancelled out. As if now let's do the force balance stuff. This will be equal to mv square divided by r. Okay, so r will be this distance, right? Okay, so r will be the distance. See, v square by r will be the velocity of the car, and then the r will be the radius with which the car is going to make that turn. Okay, so that will give me the centripetal acceleration. So same acceleration will act on this bob in the opposite direction, right? So these two steps are oppositely related, right? Next force will be the gravitational force, that will be like mg, that is going to act downwards. Okay, so then the next component will be the tension that is going to hold these two, that is going to balance these two forces, right? Obviously you are just having a pull towards the right because of the fictitious force, and same way you are having mg that is going to act downwards. So if you do not have any tension to hold this one, this will obviously fly off. That's not going to happen. Therefore there will be a tension that is acting such that it is going to balance these two forces. Okay, so now I could actually split this component into two, right? Vertical and then the horizontal stuff. If I do it in such fashion, you will have this one tension that is going to act upwards. You will have some component, right? Same way, I could split it horizontal also, fine. So now I'm just worried about the theta. Where should I put the theta? The angle that it has made between the vertical and then the wire is this one. So that's the theta which I'm supposed to find. Okay, so here it is clear the angle made by the wire with the vertical is. So I just need to get the angle that is made between the wire and then the vertical. Okay, so this is my theta which I need to find. So if this was like theta, obviously the alternate angle will be like this one will be my theta, right? So this component is also theta, so this one will also be theta. Okay, so then obviously this vertical one will be like t cosine theta, and then this horizontal one will be like t sine theta, right? Got it? Fine. So now I'm just done with all those vector resolution, or else the free body of that particular mass which is hanging inside the car. Okay, so that stuff is done. So now I'm just ready to equate those two x-axis and the y-axis. I'm just ready to do the force balance along the x and then the y-axis. If I do those two stuff, I'll end up getting the theta that is required. Okay, so tt will get cancelled out and then I'll get the theta that is needed over here. Fine. So let me do it. You'll get the answer in just a single step. So summation of forces along the x should be equal to 0. It doesn't move along the x because all those forces is getting balanced, right? T sine theta will balance the mb square by r. So that is when this will come to rest. Okay, it will just swing a little bit and then it will come to rest. Okay, until the car is in turn. Once the turn is completed, there isn't any frictional force that is actually centripetal force that is actually needed. Therefore, the car will start moving in a straight road, straight. In that situation, the bob will come to the mean position. Okay, but here the car is still in the turn. Therefore, externally there is a force that is acting radially inward. Inside the frame of reference, there should be a force exactly opposite to that of the inward force. So that is going to be like radially outward centrifugal force or fictitious force. Okay, that logic should be clear. So summation of forces along the x should be equal to 0. Same way, summation of forces along the y should also be equal to 0. So both those things has to cancel out each other. If that was the condition, then you will have t sine theta, which will be equal to m v square divided by r. Same way, t cosine theta will be equal to mg. Okay, so now I'm just supposed to find the theta, right? So either I could equate the t or else let me take the ratio. You'll get it in a single step. So sine t sine theta, just divide the left hand side by left hand side, right hand side by sine right hand side. So you'll have sine theta divided by cosine theta. That's going to be tangent theta, which will be equal to mv square by r, mv square divided by r divided by mg, right? So these two things will get cancelled out. M will get cancelled out. If I rearrange this equation, I'll have v square divided by rg. Okay, so now I'm just ready to substitute all those data that is given in the question. You have like velocity of the car to be like 10 meter per second. Same way you got the radius of the car to be 10 meter per second, 10 meter, and obviously g will be like 10 meter per second square. The length is something that is not needed in this case to solve the question, so that is something extra data that they given. Okay, so if I do substitute those things, instead of v I'll plug in like 10 into 10, and then you have radius to be like 10 and the same way g to be like 10. Okay, so it get cancelled out, everything get cancelled out, and then I'm just left with 1. Tangent theta will be equal to 1, so theta will be equal to tan inverse of 1. Okay, so tangent inverse of 1 is like 45 degree, therefore theta over here is 45 degree. The answer is theta will be should be equal to 45 degrees. So 45 degree is like pi by 4. The option here is 3. That will be my answer. Okay, so you shouldn't have any doubt in this question. So this is simple easy one only actually, because the only trick that you need to know in these kind of sums. Okay, so when you have centripetal force acting externally, the object will move in a circular path. Okay, if you look at the same object from internally, which means from the inside frame of reference, in that situation every object that is inside that frame of reference will be thrown outwards, radially outwards. Okay, so you will experience a force that is exactly opposite to that of the force that is getting acted in externally. Okay, so those two things will be opposite to each other. Okay, so that's the intuitive thinking that you need to know. Okay, so you should be clear with this question. You shouldn't have any doubt. Let's move on to the next one. This question is a simple one. You have got a car of mass 100,000 kg negotiates a banked curve of radius 90 meters on a frictionless road. Okay, so there is a car that is going to take a turn, okay, on a banked road. So the road is also frictionless, which means you do not want to worry about that mu s. Okay, so I do not want to use that big formula, that bigger one. Instead, if the banking of the angle is like 45 degree, the speed of the car is, so what should be the speed with which I could actually travel so that I do not get thrown away from that banked road. Okay, in this condition, in this situation, you do not have friction to support the motion, so only because of that banking I'll have to make the turn. Okay, so if that was the case, just use the formula that we know from the theory, which is like v that is equal to root of rg tangent theta. So that will be equal to root of, instead of r I'll plug in 90. Okay, for g let me put in like 10 tangent theta, so tangent 45 degree, that's going to be like 1. Okay, so if I just take it out of the square root, you will have like 3 0. That's going to be 30 meter per second. Okay, the answer here is option 2. Simple sum. It should be clear. Let's move on to the next one. This sum is like a straight away sum. Okay, just get the formula, you'll get the answer. That's it. A car of mass m is moving on a level road. Okay, so this is like an horizontal level road, circular track of radius capital R. Okay, if mu s represents the static friction between the road and the tire of the car, fine. The maximum speed of the car in the circular motion is given by, so with what maximum speed it could actually make the turn. Okay, we have already learned in the theory, right? That should be like option 4, mu s root of mu s r g, right? It should be clear, right? If you are clear with the theory, you should understand this sum. Okay, it should be clear. Let's move on to the next one. This question is also based on the fictitious forces. Let's see what the sum is. A gramophone record is revolving with an angular velocity omega. Okay, so there is a gramophone record which is revolving. This is a kind of circular disc that is revolving with an angular velocity omega. Fine. So you may have seen in any animated movies or cartoons. So gramophone record is actually the old style audio storage device. Okay, so this will, from this device I'll be able to play the music. Okay, this is kind of like an old stuff. Okay, 1970s 1960s or like somewhere around 1930s you had this kind of device. Okay, to store the audio files. Fine. So this is like a circular disk, and then you have a pin that is placed above the disk. Based on the movement of the pin, it will generate the audio. Okay, so that's an audio storage device. Got it? So anyway, end of the day, what you need to know is gramophone record is actually a circular shaped disc. That's it, finished. A gramophone record is revolving with an angular velocity omega. A coin is placed at a distance r from the center of the record. Okay, so from the center of the record at a distance r, I'm just going to place a coin. Okay, that's the second statement. The static coefficient of friction is mu, so the friction between the coin and then the record is like mu. The coin will revolve with the record if. So what they're asking us to find is the coin should revolve along with the record without any relative motion between the coin and the record. Okay, so if for someone who is standing inside the gramophone record and looking at the coin should be at the same position with respect to the coin, with respect to that disc. Okay, so if that was the case, the coin should not toss over from its position where it has been placed, or it shouldn't get thrown over from the point where it has been placed. Okay, so what should be the r, what should be the maximum r with which the friction could actually balance that coin while the entire system is in circular motion, right? So same thing, same way like the previous sums here, instead of that circular drum or those kind of sum, here they have given us the disc, and on top of the disc I have placed the coin. Okay, or the car that is going to turn. Okay, we have seen like multiple sums, right? So it's a kind of same sum, but the thing is here I'm just going to place the coin over the disc, and that coin should be at rest with respect to the disc. Therefore the frictional force should be good enough to balance the disc, to balance the coin from getting thrown away from that particular point. Okay, so it should not fly off from that particular point, right? Got it? So let me draw the diagram, and I'll tell and I'll put all those forces that is involving in that particular coin. So once you get the free body diagram for that coin, we'll be able to solve it easily. Okay, so now we have got a gramophone record. Okay, so this is a kind of circular shaped disc. Okay, this is kind of disc. Okay, and then you have got a coin that is placed at a distance of r from the origin. So you have got a coin over here. Got it? So the entire disc is spinning with an angular velocity omega. If that was the case, the coin that is inside the disc will experience a centrifugal force. Got it? It will have a fictitious force to move away from that position, right? So it will experience a fictitious force with an acceleration of v square by r. Okay, so here in this question it is pretty obvious, everything comes with like omega. So instead of using mv square by r, I'll just use like, for the easy solving, I'll use like mr omega square. So that will be this fictitious force that this coin is going to experience radially outward. Okay, so this wants to move away from the origin with an force of mr omega square. Okay, so this, when you look at this coin from inside the frame of reference, this wants to be thrown away from the origin radially outward. Okay, that shouldn't happen. Then what should be there? You should have a frictional force that is acting radially inward to balance this one, right? Obviously, if this wants to fly away, someone has to push it in so that it is in that particular position with respect to the disc, okay? So who is going to push that one in? In the drum case, it was actually pushed in by the wall of the drum, okay? So in the car case, the tension in the string was able to balance that mass. So in this situation, obviously, frictional force should balance this fictitious force, okay? So here, frictional force will just support it. This stuff didn't move, therefore the frictional force will be like the static frictional force, okay? So here the frictional force will act inwards, okay? Static frictional force is going to act radially inwards, and then you will have these two components, right? One will be like the normal one and the other one will be like the mg, okay? So these are the four forces that is acting along two-dimensional plane, okay? So you have got like mr omega square and f in the x-axis, and along the y-axis you have got like n and then the mg, okay? So now everything is done. So this entire coin is at rest for someone who is standing inside the disk and looking at the coin, okay? So it will be at the same position with respect to the disk, okay? Then obviously all those forces should be balanced, okay? So summation of forces along the x should be equal to 0. Same way summation of forces along the y should also be equal to 0, okay? Summation of forces along the x and y should be equal to 0. If that was the case, for the first step, frictional force is acting towards the negative I cap, something like that. So minus f s plus mr omega square should be equal to 0. Same way here, n is like upwards, minus mg should be equal to 0, okay? So if we do the rearrangement over here, you will have like n that is equal to mg, obviously. Here, instead of static friction, let me substitute mu Sn, right? Okay, so they have given the static coefficient of static friction as mu. Okay, so you have got mu n, which will be equal to mr omega square. Okay, what they're asking us to find here is actually the r. Okay, so I'll just rearrange it according to the r. Fine. So if I do the rearrangement thing, you'll have mu, got it? Instead of n, I'll substitute like mg, which is equal to r divided by m omega square. Okay, so let me cancel these two stuff. M, let it get cancelled. So you'll have like mu g divided by omega square, right? So mu g divided by omega square. Fine. So r should be equal to mu g divided by omega square. If the r was equal to mu g divided by omega square, then obviously I'll be able to balance this coin, okay? So if r was greater than this particular parameter, then what will happen? If r is going to be greater than that stuff, then obviously when r is going to increase, then obviously that centripetal, I mean like fictitious force is going to dominate, okay, when compared to that frictional force. So obviously if I'm just going to move this coin away from the origin more and more, if that was the case, then the fictitious force that is going to act on that particular coin will be greater when compared to the frictional force, okay? Because that's the maximum r up to which the frictional force is good enough to balance that coin. If I'm going to cross that distance r, then obviously I'll not be able to balance, because as you move radially outwards, the velocity or the angular, I mean like the r will keep on increasing, right? So once r increases, the centrifugal force that is getting experienced by that coin is going to increase, but I have reached the saturation point with respect to the friction. Therefore, I'll not be able to balance, okay? So either r should be equal to this value, or else r should be less than this one, okay? So the answer will be like r should either be equal to this one, or it should be like less than that one. Okay, that is one. I'll be able to balance this one. So r should be either equal to or less than mu g divided by omega square. Fine. There is another one perspective by which you could actually get into this result. So that is something like this. So here, let me write an extra one step to it. Okay. So if I do the rearrangement thing, Fs will be equal to mr omega square, right? So if you consider this step, if the maximum frictional force was equal to mr omega square, the frictional force will be good enough to balance the coin at that point itself. Got it? If the r was greater than that one, then obviously if the r was greater than the maximum frictional force, then frictional force will not be able to increase. Therefore, the coin will be thrown away from that position. Okay. right? If the R is less when compared to this maximum frictional force, then obviously this maximum frictional force, let us keep it this way, the maximum frictional force that could be generated is like 5 Newton, okay? So R is placed such that the centrifugal force that is getting experienced is like 3 Newton. Even in that situation, the frictional force 3 Newton will be generated. Those two things will balance and the coin will be at that particular position because still it hasn't peaked, okay? Even if I just increase the R little bit, still it will be able to balance, okay? So therefore, if Fs is equal to mr omega square, still it will be able to balance, okay? Or else if this term is greater when compared to mr omega square, which means still you have like much more, still this value is less when compared to the maximum frictional force. Even in that situation, the coin will be static, okay? It will not get thrown off from that position, okay? So therefore here, so either it could be equal to this value or else frictional force, or else still maximum frictional force hasn't been reached, okay? So even in that situation, the coin will be in static condition, okay? So therefore it will be like greater than or equal to, in the next step also I'll get like greater than or equal to, so in this step also I'll get like greater than or equal to, then when I'm going to change the sides, okay, left hand to right hand, right hand to left hand, obviously this is open towards this term, therefore the less than symbol, actually the greater than symbol will become the less than symbol, okay? So R should always be less than or equal to this mu g divided by omega square, okay? So you should be clear with this understanding. What I have explained you over here is R is the maximum value with which the frictional force could actually balance this one, okay? So if R is less than that maximum value, still frictional force hasn't peaked, okay? So frictional force will be less when compared to that of this maximum value, okay? Even in that situation, frictional force will balance itself, therefore the coin will not get thrown away from that position, right? So you should get this logic, or else like straight away, as I've already told you, if R is going to increase, then obviously more amount of fictitious force will get generated, friction will not be able to balance. Therefore, R should either be equal to this value or else lesser R is possible to be balanced, okay? So that's the notion that you need to know, fine? So you should be clear with this sum. So this is a kind of thinking, logical thinking based sum, right? So the answer here is R less than or equal to mu g divided by omega square, right? So R less than or equal to mu g divided by omega square will be my answer, right? This sum should be clear. You shouldn't have any doubt in this sum. Let's move on to the next one. Next sum is two bodies of mass 4 kg and 6 kg are tied to the ends of a massless string. So I have got like 4 kg and 6 kg that is getting tied to a string. That too it is massless, fine. The string passes over a pulley which is frictionless. So it is passing over a pulley which is like frictionless, fine. The acceleration of the system in terms of acceleration due to gravity is, so what will be the acceleration of this system? Okay, so I just need to find the acceleration with which this is going to move. Obviously 6 kg will move downwards by some acceleration. For the same amount, this is going to move upwards. What they're asking us to find here is the acceleration, that magnitude, okay, with respect to g. Is it going to be g by 2, g by 5, or g by 10, whatever it is, okay? That is obviously not going to be equal to g because those two things are getting balanced one or other way, right? So here if I just consider the 6 kg mass, it will experience a downward force of 6g. So some amount of that 6g will get balanced by the tension in the string that will act upwards. Obviously this is not going to fall off with an acceleration of g because this 4 kg mass is actually balancing some part of it, therefore there is going to be an upward tension, so that is going to resist the motion of that 6 kg mass which is going to fall down, okay? So same way that in the other case you will have like 6 kg 4g that is acting downwards. Obviously you will have tension that is going to oppose this fall, so that tension will act opposite to that of this fall, okay? So this should be clear, okay? So this one pulled it upwards. In turn, this 6 kg mass also pulled the 4 kg mass upwards, okay? So got it? So in this situation, as both are hanging, this tension is going to pull both those masses upwards, so that one is going to, so in that situation, one is going to fall slowly with an acceleration a for the same amount that this 4 kg mass will move upwards with an acceleration of a, okay? So now I just have to find what is that a, that's what I'm supposed to find over here, right? So now I'm just done with the free body diagram with respect to the 4 kg mass and then the 6 kg mass. Now let us do it. So here in this case, I obviously know 6 kg mass is going to dominate, therefore here acceleration a will be acting downwards. with relation to 6 kg mass, same way with respect to 4 kg mass, the acceleration will be like acting upwards. Okay, so this is something that you need to know. So if that was the case, let me do the force balance for the first 4 kg mass. Okay, so that will be equal to tension, that will be upwards, minus 4g, which will be equal to ma, that will be like upwards. Okay, so the first thing is done. What I need to find here is the acceleration a, so that I'll rearrange it according to the tension. So I'll have like T, which is equal to ma plus 4g. So the first part is done. And for the next equation, it will be like T minus 6g, which will be equal to, so here let me substitute the mass over there. Okay, so here m will be equal to 4, right? So let me put the mass over there. So that will be like 4a. So here also you'll have like 4a. Yes, so 4a. In this case, it will be like T minus 6g, and then you'll have like minus 6a. That will be directed downwards, right? Minus 6a. If I do the rearrangement thing, you'll have like T, which is equal to 6g minus 6a. Yeah, right. If I equate those two tension, I'll get the answer. So if I do equate those two stuff, you'll have like 4a plus 4g, which will be equal to 6g minus 6a. So what I need to find here is actually the acceleration. So if I do the rearrangement thing, you will have 10a, which will be equal to 2g. Therefore, acceleration a will be equal to g divided by 5. Yeah, that's right. Acceleration was equal to g divided by 5. The answer here is option 3, right? So you should understand this question. This is like a simple one only. In both those situations, the tension was actually pulling it upwards, right? Because both were hanging downwards, therefore both are getting attracted downwards by acceleration due to gravity. So due to gravitational force, therefore tension will resist the motion of the gravitational force. So with respect to the smaller mass, the tension was good enough to pull it upwards. With respect to the heavier mass, the tension was good enough to balance it to a certain extent. Therefore, that was actually accelerating downwards. So whatever the acceleration with respect to one mass, you got the same acceleration magnitude on the other mass, but in the opposite direction. Okay, so that's what you need to know regarding this question. It should be clear. There shouldn't be any doubt on this question. Let's move on to the next one. Next question is something that we have already discussed in the theory. Okay, so case 4 of the fictitious force. So you're going to place a mass on the inclined plane, and then it is going to accelerate. What should be the acceleration with which it has to travel so that the block doesn't slide in that wedge? Okay, same question, easy. Fine. So I'll just read the question. This is like a same condition of the case 4 of the fictitious forces that we have seen in the theory part. Okay, so here you have got like a block of mass m is placed on a smooth inclined wedge. Okay, smooth, which means there isn't any friction. Fine. Case 4. Okay, if you are strong in the theory part, you'll get the answer straight away. A block of mass m is placed on a smooth inclined wedge of inclination theta as shown in the figure. The wedge is given an acceleration a towards the right. Okay, so it is moving towards the right. The relation between a and theta for the block to remain stationary on the wedges. So this is like a smooth inclined plane, which means there isn't any friction. That was the first case that we did see in the fourth case. That was the first section. Okay, so the answer that I got in the theory was like a equals g tangent theta, right? So that's the answer here also. So if you are going to travel with that g tangent theta acceleration, then the block that is on the wedge will not fall down. Okay, even if you do not have any friction, it doesn't matter. It will, that one component will be good enough to balance that mg sine theta, right? So you should be able to understand this one. It's an easy straightforward sum if you are thorough in the theory. Okay, so let's move on to the next one. This question is also based on balancing forces. Okay, let's do the sum. A balloon with mass m is descending down with an acceleration a. Okay, so balloon is actually descending down with an acceleration a. Okay, where a is less than g. Fine. So acceleration with which it is descending down is not equal to the acceleration due to gravity. It is less than g, which means the upward thrust force is given by the surrounding air. Okay, while drawing diagram you will get it. How much mass should be removed from it so that it starts moving up with an acceleration a. Okay, so if I remove certain amount of mass, it should be able to ascend up. Okay, so the force given by the surrounding, which means the wind force should be good enough to move it up, to move the balloon up. Okay, so how much mass should be removed? That's what I need to find over here. Okay, it's a kind of hot air balloon stuff. Okay, so here you have got two balloons. Okay, so two different conditions. Initially, the mass of that balloon was like equal to m. Okay, so in this situation, what will be the force that is acting on this particular balloon? Mg will be like acting downwards. Same way, because of the surrounding air molecule and because of the wind, okay, this stuff isn't like falling down with an acceleration of g. Instead, it is like falling down with some acceleration that is less than that of this g. So the acceleration with which it is falling down is actually equal to a. Okay, it is less when compared to this g. So if there wasn't any surrounding molecule, or if it wasn't the vacuum, it will just fall down with an acceleration g. But that's not the case here. You are having like surrounding air molecule that is actually pushing this one a little bit extra upwards. So you are having an upward force. Okay, the force isn't good enough to make this balloon move upwards because mg is dominating. Therefore, this is like descending down slowly with an acceleration a. So that's the first condition. Okay, so in the second condition, what I'm going to do is I'm just going to remove some amount of mass. That's what I need to find. How much mass should be removed from it so that it starts moving up with the same acceleration. So in the second case, I've just removed some mass from this initial mass. Okay. So in the second condition, I actually removed m minus m naught. So m was the mass that was initially in the balloon. I just removed some mass from it. So here it will experience gravitational force of m minus m naught into g, but the surrounding wind condition is just the same thing. Okay, so the wind is going to push this one up with the same amount, right? So the surrounding wind condition is just the same, therefore the wind is going to push up by the same amount of force F. So in both those situations, the upward force was just the same thing. So that's the trick with which I'll be able to solve this sum. Okay, so I've just removed someone. So in the second case, it started accelerating upwards with the same magnitude of acceleration with which it was descending down in the first situation. Okay, so now I'm just ready to do the like force balancing stuff. Free body diagram is done. So once I do the force balancing stuff, if I just equate the F, I'll end up getting the M that is needed. Okay, got it? So simple, easy. So just do the mathematical stuff, you'll get the answer. Okay, so here with respect to the first balloon, you have got F that is going to act upwards minus mg that will act downwards, which will be equal to ma minus ma, negative of ma, right? Minus ma. In the second case, you'll have like F, which will be equal to m minus m naught g. Okay, that will act downwards. Same way. Oh no. F that will act downwards, right? F minus m naught g, which will be equal to the acceleration that has been produced that is going to be acting upwards. Okay, so that will be like m minus m naught a, that will act upwards, right? Now I'll be able to equate these two F. Obviously the upward thrust force is just the same for both those balloons. The upward force was given by the surrounding air molecule and the wind, so you are going to have the same upward thrust force. Okay, so that is the same. Okay, so if I do equate those two equations with respect to F, I'll end up getting equation something like this. So if I do equate for the first one, it will be like mg minus ma. I've just rearranged this one and then I substituted the first f. Okay, which should be equal to, which will be equal to m minus m naught a plus m minus m naught g. Okay, so what I need to get over here is the m naught. So how much mass should be removed? That's what I need to get, right? How much mass should be removed? So m naught is something that I need to find. Therefore, just do the rearrangement thing, you'll get the answer. That's it. M naught is something that I need to find. Okay, now let's do the inner multiplication and cancel out the stuff that is same on the left hand and the right hand side. So if I do the inner multiplication, you will have like ma minus m naught a plus mg minus m naught g. Okay, so mg will get cancelled out. negative MA will not get cancelled out, okay? Yeah, so I'll have to put the M naught on the one side and M and A on the other side, okay? So if you do the rearrangement, you will have, you got like 2 M naught, right? So let us move these two stuff towards the left hand side. So you will have M naught of A plus G, M naught of A plus G, which will be equal to MA plus MA, that will be like 2MA. Got it? Therefore, M naught will be equal to, I got the answer. M naught will be equal to 2MA divided by M naught A plus G. 2MA divided by M naught A plus G. 2MA divided by, okay, so I've got like 2 M naught, so that's all. Yeah, M naught will be equal to 2MA divided by A plus G. So we'll have like 2MA divided by G plus A. So that will be like option 1. So the answer for this question is like option 1, right? So this sum is also like a pulley based sum, okay? So we did pulley in that in the before cases, right? So same way, you just put force balance for those two conditions, just do the force balance thing, then look at that sum, whether it is accelerating or the acceleration is 0. In this situation, it was accelerating with some acceleration. So right hand side of the force balance equation should be we should put some acceleration into it. So direction should be properly mentioned, so should be properly specified. If it is like downwards, it should be put negative. If it is like upward, it should be put positive. If you don't go with the sign convention properly, you'll end up getting the wrong answer. So you have to be careful with the signs, right? Then solve it, you'll get the answer M naught, right? You shouldn't have any doubt in the sum. This is a little bit lengthy and tricky, okay? It should be clear. Let's move to the next one. This sum is based on lift. Let's read what the sum is. A person of mass 60 kg is inside a lift of mass 940 kg and presses the button on control panel. Okay, so the mass of the person was like 60 kg and the mass of that lift was equal to 940 kg. Okay, which means altogether it is like 1000 kg. So that is what that lift has to pull up. Okay, the lift starts moving upwards with an acceleration of 1 meter per second square. So this lift starts accelerating upwards with an acceleration of 1 meter per second square. So that was given, fine. What they're asking us to find is the tension in the supporting cable. So what should be the tension that is acting in the supporting cable, okay? So if you just read this question really properly, you'll get to know that we are not going into the frame of reference of that lift, okay? We are just looking from the outside and looking at the lift, okay? So when you look at the lift, there is an object that wants to move upward with an acceleration of 1 meter per second square. So what should be the upward force that is acting on that lift so that it is able to move upward? So that upward force is nothing but the tension in the rope, right? Once I draw the diagram, you'll get it clearly. So here you have got a lift and then there is a guy who is standing inside. The weight of that, the mass of that person is like 60 kg. Same way, the total mass of the lift is like 940 kg. Altogether, this sums to 1000 kg. Okay, so there will be a downward force because of this entire setup will be equal to 1000 g. So that will be the downward force acting on this lift and then the person. Okay, so I just have to move this one upwards with an acceleration of 1 meter per second square. So it is going to move upward with an acceleration of 1 meter per second square. Okay, so this entire system has to move upwards with an acceleration of 1 meter per second square. Then what should be the upward force that I need to give to this object? Okay, so that will be given by the rope. Okay, so tension in the rope will give you that upward force, right? So here upward force is nothing but the tension. 1000 g is the downward force. Because of this extra tension force, this entire setup is going to move upward with an acceleration of 1 meter per second square. It's a simple sum, right? You're having an object, it wants to move up, okay, with some accelerations. Then what should be the upward force that I need to give? Here the upward force is given by the tension in the rope, right? Simple sum. So you do not want to think deeply into that fictitious stuff and all those things. Only when you are going to study for a person that is standing inside the lift, this thing comes into picture. That fictitious force and all those things. Whatever effect that is happening outside will have a counter effect inside us. Okay. So that thing will come into picture only when you are going to study that person. Here I am not going to study the person. I'm just going to study that entire setup. Therefore, just do the force balance stuff, you will get the answer. Okay. So if I do the force balance thing, you will have something like this. T that is acting upwards minus mg that will be like downward 1000 g, which will be equal to mass of the entire setup is like 1000 and the acceleration will be like 1 acting upwards. Okay, so T minus 1000 g will be like this one. So tension in the string will be like 10,000 plus 1000, right? So here they have given us straight away to take to be like 10 meter per second square. Therefore, T will be equal to 10,000 plus 1000. So T will be equal to 11,000 newtons. So tension in the string, the tension that is needed in the string should be equal to 11,000 newton, which is nothing but the option 3. Okay. You should be clear with this sum. You shouldn't have any doubt. Let's move to the next one, which will be the last sum for this session. This sum is also same as that of the previous sum. Here you have got the mass of a lift is 2000 kg. Okay. When the tension in the supporting cable is 28,000 Newton, then what is its acceleration? So same stuff. You have got a lift whose mass is like 2000 kg. Therefore, you will have 2000 g that will act downwards. The tension in the cable will be like T that will be equal to 28,000. I mean like 28,000, right? So 28,000 Newton. If that was the case, then its acceleration will be obviously this is going to dominate. Therefore, if I if I force balance it, I'll have like 28,000 that is acting upwards minus 20,000 including that g, which will give me the mass times acceleration. The mass was like 2000 times the acceleration. Okay, so this will give me the acceleration a. I do not put any sign into it. Even though I know it is like accelerating upwards, that doesn't matter. I didn't give any sign. So while solving this equation, I'll end up getting the direction. Okay. So if I do solve this one, you will have 2000 A, which will be equal to 8,000. Okay, zeros will get cancelled out. 0, 0, zeros, 0, 0, zeros, and then 2, 8. Those of stuff will get cancelled out. Therefore, A will be equal to 4 meter per second square. So the term is going to be positive. So initially I took it as positive. The direction was correct. Therefore, I got the answer to be in positive, which means this entire mass will be lifted upwards by an acceleration of 4 meter per second square. Okay, so 4 meter per second square upwards. So that will be my answer, which is like option 1. So by this time, you should be clear with the sign convention and all those things that I'm doing. Okay, you shouldn't have any doubt in that sign convention stuff. So only one parameter is unknown. In that situation, take it as positive. If the direction is right, you'll get the answer to be positive. If the direction that I took was like wrong, then I'll get the answer to be like negative. Okay, so that's the intuition that you need to know while putting that signs and all those things into the equation. Okay, so you should be clear with the sums that we have solved in this session. You shouldn't have any doubt. Just go through this sums multiple times so that you get a clear picture of all those sums that we have seen. Okay, because these sums will be the foundation for the rest chapters. Fine, only when you are thorough with that sign convention, force balancing stuff, the rest of the chapter becomes easy, right? So you should be clear with the sums that I've taught you or in this session. So next session we'll have around like 10 11 sums. Okay, with that all the PYQs that are related to laws of motion chapter will get completed. Okay, so with this the video gets completed. Bye.